All right, how's everyone doing?
Good.
There's like twice as many people here as the last section. That's good. All right, any issues with the ODP? All right, so here's a solution for the ODP, and as I said, basically two assignment statements. So set is your function; it's taking a pointer to a struct node. So in arrow data says take the data field of the struct node to which in points. All right, so in arrow data is the same as star in dot data. Take the thing to which in is pointing, that's a struct node, look at the data field. So that reads the data field, multiplies by 2, stores it back in the data field, and then it stores a null in the next field. Okay, so you're not malloking anything, you're working with a node that already exists. And definitely not printing anything or anything like that. Now, if you accidentally do a malloc and create a new node, your test program may look like it's doing the right thing because you're going to start off with a node and you know, if you malloc a new node and set the data equal to 2 times that, right? But it's supposed to be the original node. Yeah.
So when we're like declaring at the top in the struct node thing, like struct star next, and then in the function we have like struct node star in. Is it the same thing, but we're just using a different name?
Well, up here in the struct node, we're defining what this structure is, right? But this piece of the structure called next, it's saying that next is the same type of thing as the argument we're passing to this function, right? Which kind of makes sense because the next field in here is supposed to be a pointer to a node, right? And what we're supposed to be passing to our set function is also a pointer to a node.
So are they pointing to the same place?
Not necessarily, right? It depends what you pass to set. If I say set haha, whatever haha is pointing to, that's what in is going to be, right? That address. This up here isn't actually a variable, right? This is a blueprint for what a struct node will look like when you make one. But there's actually nothing being created here. There's no data being initialized. There's no locations in memory being chosen. This is really just saying this is what a struct node is. It's like saying an integer is a thing that's 32 bits across, right? It's a description of what a struct node will look like, but there really is no value for data in that highlighted block, right? Until you actually create something that's a struct node, and then you can talk about its data field. When we get to objects in 223, right, this will become a little more severe, this distinction between that struct node statement, which is a description of a struct node, versus actually using a struct node. So we'll talk about classes and objects, and a class will be that highlighted block, the blueprint for what we'll eventually call an object. All right, so ODP 206. So 206, we're going to keep working with this idea of dynamically allocated nodes. So you're making a function called new node, and new node is basically responsible for creating a new node out of thin air. And this version of new node also lets you give it a data value, and it will initialize the data field of that new node to be data, and it will initialize the next field to be null. So the prototype is struct node star new node int data. So that's what your function should look like. So if I say something like struct node n equals new node 1, 2, 3, 4, 5, here's what new node should do. It should find a block of memory that's available. It should reserve it. It should think of it as a struct node. It should set the data field to 1, 2, 3, 4, 5. The next field to null, uppercase NULL. And then it should return the address of the beginning of that block of memory. So up here, n would now be a pointer to that struct node. So new node allocates a block of memory, sets the data field, sets the next field, and returns the address of that block as the function value. And if you're writing a program to test it, make a struct node. This has to be a star. It's got to be a pointer to a struct node. Set that equal to the return value. And now if I look at n arrow data, it should be 1, 2, 3, 4, 5. If I look at n arrow next, it should be null. All right, so that's all there is to 206, but again, you got to get it lined up just right. So you will be doing a malloc in here, right? You'll be creating a new node, and then link it with the test bed and assess it as usual. So I'd like to play with some of this code today. I want to start writing some more code that uses this idea of malloc and lets us create a set of nodes and build them together into a linked list manually. And we'll use that to play with a print function. And we'll talk about some of the mechanics of freeing memory that we allocate. And we'll just kind of get our hands more dirty playing around with this stuff in C code. And then tomorrow, or Friday, I want to talk about PA2. No class tomorrow, remember. Friday we'll talk about PA2. And as far as I know, I'll be here Friday. If anything comes up, I'll post something through Clark's website, and you should get a Canvas notification. But 90% chance I'll be here Friday. All right, so here's some list code, and I did something similar in the previous section, and I already posted that code on Canvas under the code area. So this was kind of our code from yesterday. We've got our struct node, the usual structure, data, and next. I'm going to keep using this typedef of a struct node to be a linked list. I've got the init function, which we're using to create a sentinel node. And my main program is 2 lines. Declare a list to be a struct node star, and then give it a value by calling init. And the init function has a struct node star, which I'm calling sentinel. I set its data value to 42, set its next value to null, and return that. Okay, so this we did yesterday. But this is really close to what we need to do to make our get node function. Or our new node function. I don't want to write new node for you. Okay, so we're just going to write a get node. New node is a little different because it sets the data value to the integer you pass, and it sets the next value and so on. But I want to make something like our get node function from PA1. So remember PA1, get node, what does it do? It finds a block of memory that it can use, a location in the array. It sets the valid flag to 1, which is marking it as in use, and then it returns the index of that entry. Okay, that's basically what our get node is going to do. So in PA1, to find a block of memory that was available, we made a loop. We started with the beginning of our array of struct nodes. We looked through it until we found a spot where valid was equal to 0. We said this block of memory is not in use. We marked valid to 1 to say now it's in use, and we return the index of that block. That's basically what malloc does. When I call malloc and I say give me 12 bytes of memory, it goes through its internal data structures and it looks for a block of memory that's not in use, effectively where the valid flag is 0. And then it sets that valid flag to 1, effectively, right? It updates something to say now this block is in use, and then it returns the address of that block. Well, that's basically the index in the array. So, and if we run out of memory, in PA1, what do? We returned my null as a special flag saying we're out of memory. Well, malloc will return null if it's out of memory. And so we're going to have getNode return null if it runs out of memory. So we'll say return null if out of memory. Well, this is a one-liner. All right, malloc does all of that work for us. So size of struct node says how many bytes of memory do we need to store a struct node. Pass that to malloc. Malloc will find that chunk of memory. It'll mark it as in use. It'll return the address of that block, and then we'll return that as the value of getNode. And if we're out of memory, malloc will return null. So by returning malloc's value, we'll be returning null. So this is one of those places where I wanted getNode to do something very specific in PA1, because all you got to do is replace it with a call to malloc, or just make a getNode and wrap malloc around that. So let's prototype this function. So getNode creates a new but uninitialized struct node. ODP 206, you're initializing it. So let's make a linked list call first. That's a pointer to a struct node. And let's set it equal to getNode. And let's just try that in GDB. All right, so compiling list.c, calling the output executable list, and -g says include GDB support. And so I can run list, and it doesn't do anything because I didn't print anything out. If I want to run it in the debugger, just put GDB in front of the command, GDB list. And this reading symbols from list done down here tells me that I compiled it with G, so it's actually ready to help me with debugging. If you try to use GDB on something that wasn't compiled with a -g switch, like /bin/ls, you get the symbol down here, reading symbols from bin ls, no debugging symbols found. Okay, for your code that means you probably want to go back and make sure you recompile with -g. You don't need it, right? I can start debugging the ls command, but without debugging information in there you don't get very far. But you can have fun with that. All right, so let's GDB list. So I'm going to say start, and first thing I'm going to do is call init and save the result in list. What is list before I do that? It's some memory location. When you see a bunch of F's, usually with a 7 in front, that's probably a location on the stack. That's a local variable. Right? You just kind of get to know that after doing this enough. if I print the thing that list is pointing to, it tells me it's pointing to a struct node with a data value of 1 and a next value of some other weird location. That's random. Okay. So let's say next. And now, if I look at the value of list, it's a nice, reasonable looking address, hex 602010. And if I say print the thing that list is pointing to, it's a struct node with a data value of 42 and a next value of null. That's our sentinel. It's right there at location 602010. All right, so I'm going to declare first to be a linked list, and I'm going to set it equal to the return value from get node. If I look at first right now, it's a 0, right? It hasn't been initialized. If I try to look at the thing that it's pointing to, it's a segmentation fault. I can't access memory location 0. So I'm going to say next, which is going to execute instruction 18, first equals get node. And now if I print first, it's another nice memory address, 602030. And if I look at the thing that first is pointing to, well, that's not very interesting. The data is 0, the next is 0. Remember, get node is returning an uninitialized node. Happened to be 0, but if I do it again, it might be weird numbers. All right, so that's all our program does right now. So let's make it do more interesting stuff. So we've got list with a data value of 42 and a next value of null. And we've got first with an unknown value in data and an unknown value in next. Let's make a linked list containing one node. So what value should we put in the data? Somebody give me your favorite integer. 2. All right, how do we put a 2 into this block of that node called first?
You would have list that next point to first.
Well, let's just put a 2 in here first.
Okay. First dot data equals 2 after having initialized first as a.
Right, so we called new node, so first is pointing to a struct node. And we want to set its data field equal to 2, right? So the only thing I would change on here, we want the thing that first is pointing to, we want that data field to be set to 2. And this is the thing that we have a special syntax for, which is first arrow data equals 2. So when I'm thinking of these nodes, if this is some node n, this block up here is n arrow data. This block down here is n arrow next. N equals the address of this block. So when we look at first and we see that it's hex 602030, it means that memory location 602030, we find the data value of this node. In code, we can get to it by saying first arrow data. And then sometime after that in memory, probably around 602038, we'll find the next field. And we can get to that by saying first arrow next. All right, so we can set the data value like this. All right, and then we want to connect this into a linked list. So we want list's next pointer to point to first. So this is what you started to say a moment ago, I think.
Okay.
So how will we make this block down here point to this node over here?
List arrow next equals star first.
So list arrow next, that's this block down here. That should be an address, right? It should be a pointer, which is an address, the location of this block. So if this is a struct node, right, and first is the address of that block, then really we just need to set this equal to first. So this is one of these fine details that can be really kind of slippery. Star first would be a struct node. First is the address of a struct node. Sometimes we want to deal with star first, right? When we want to actually resolve a field, we want to pull off the data piece of that. We could say star first dot data, right? Or first arrow data. But sometimes we want to actually use the address, typically when we're linking these blocks up. So list arrow next equals first actually sets this block to have the address of this block. So now the sentinel node points to first. So instead of being null, we've got an arrow going over here. All right, what's the last thing we need to set up? Say again?
First needs to point to null.
Yes, first needs to point to null, so we want to put a null in here. So this is first arrow next, and we just want to set that equal to null. So that'll indicate that that's the end of the list. Alright, so there's a first node. We set the data field equal to 2. We set list next to be first. We set first next to be null. Alright, so list is 60, 20, 10. If I look at star list, the data value is 42. That's the sentinel node's data value. The next value is 60, 20, 30. If we look at what's stored at location 60, 20, 30, it's the number 2. And right, that's also this variable called first, which it knows is pointing to a linked list. So if I print the thing that first points to, it knows that's a struct node. It'll show me the fields of it. So data is 2, next is 0. I can also examine memory using the X command. So at location 60, 20, 30, there's our number 2, that's the data field. And this byte down here is actually the next field. So that's a 0, that's our null. All right, everyone still with me? All right, so let's make some more nodes. Let's make a second node. Alright, so I'm going to make a node called second. I'm going to call get node. I'm going to set its data equal to, so what's somebody else's favorite integer? 7? Cool. So we're going to extend our linked list. We're going to stick a 7 over here. Yeah?
Quickly going back, so when we're saying something like first instead of first star, are we, is first like the overall like structure, and then when we're saying star first, that's like actually going
So
to
first is an address. Okay, first is a struct node, right? That's what struct node star, that's what linked list is. So first is an address. if I say first arrow next, that's like star first, the thing that it points to, dot next.
So that's like actually accessing.
That's actually
actual
accessing.
things
Within the structure, exactly, yeah. If I just say first, it's just a location in memory. So when I say list next equals first, it's setting list next equal to some hex number, which is where in memory first is stored. But when I say first arrow data, it's actually picking off the data piece of that struct node. All right, so second is a new node up here. I'll set its data value equal to 7. And then I'm going to set first arrow next equal to second. So first arrow next is this block down here. I'm going to set it equal to the address of our second node. All right, well, you know what's coming next. We're going to make a third node. So what's our data value here? 14. So third is get node, third data is 14, and we want our second node to point to our third, so second next should equal third. And this is going to be our last node, so I'm going to set third next equal to null. Well, that should give us a list of 3 nodes. So no seg faults, that's good. Let's run it in GDB. So let's stop right here. We've done our first 2 nodes. Okay, list has a data value of 32, next value of 60, 20, 30. That's where first is pointing. So if I look at first, that's got a data value of 2 and a next value of 60, 20, 50. 60, 20, 50 is where second is pointing. So I can look at second. It's got a data value of 7. It happens to have a next value of null. So far we've built our sentinel node, our first node, our second node, but this field down here is null. Okay, so we're about to execute linked list third equals get node. So if I print third, it's 60, 20, 70. It's uninitialized. Its data and next are both 0. So we're going to set the data field equal to 14. So now data is 14, and then we're going to explicitly set the next field, set second next to be equal to third. So right now, second, remember its next field is null. When we say second arrow next equals third, now if I print second, its next field is 60, 20, 70. Right? What's 60, 20, 70? That's the value of our variable third. That's the address of the third node. And then we're going to set third next equal to null, which is not interesting because third already had next equal to null. So there's third. Well, we've built a linked list. We've got a list with a sentinel and 3 nodes. But this doesn't always work. I got lucky. So list is hex 60, 20, 10. So let's make a memory map. 60, 20, 10, 14, 18, 1C, 20, 24, 28, 2C, and so on. all 6020 in the beginning. All right, so this first entry here, 602010, this is list. So I'm going to examine 8 words. So a word in this sense is 32 bits, 4 bytes. Integers are 4 bytes. On this machine, addresses are 4 bytes. So that's sort of the fundamental size that we're working with. So we call that a word. So I'm examining 8 words in hex. That's what the first X means examine memory. The slash says show me 8 bytes in hex. And here's the address I want to start at. So this is the contents of location 602010, 602014, 602018, 6021C, 602020, and so on. And I'm just going to fill in my memory map. So at 602010 I find 2A. That's a hex number, so 2 times 16 is 32, plus 10 is 42. So right here in the beginning, that's the data value of my Sentinel node. It's followed by a word containing 0 and then a word containing 60, 20, 30. Well, remember when we looked at list, it said the next field was 60, 20, 30. So we can deduce that this is the next field of our struct node. This is just filler. Why didn't it put the next field here? Because it likes things to be aligned on multiples of 8. That has to do with how memory is physically organized and how you actually take an address and use it to pull the bits out of a block of RAM. So this is our data field. That's a 4-byte int. This is filler. This is our next field. That's another 4-byte int. And then all of this is just filler because the next time we called malloc, it was 32 bytes beyond the previous call. All right, so we can fill in our memory map. This is a 42, this is a 0, this is 60, 20, 30, and these are basically unused. All right, first is the value 60, 20, 30. So let me draw a separator here. And first is basically this address in memory. And if we look at 60, 20, 30, what do we find? The number 2, a byte of filler, and then hex 60, 20, 50, and then 5 bytes that are effectively random. So this is 2, 0, 60, 20, 50, and then bytes that are unused. Let me change this 0 to a dash because it's really unused. And then second is 60, 20, 50. And if I examine memory starting from 60, 20, 50, I see a 7, filler, and 60, 20, 70. And third is 60, 20, 70. And if I examine starting there, the data stored is 14, that's hex E. And then this next field, this third word over, is a 0, that's null. So that's what our list looks like in memory. Sentinel node, pointer to next, data value, pointer to next, data value, pointer to next, data value, pointer to next, which is null. So this is list data, this is list next, and so on. Okay, this is not just for fun. This is what you actually get to do when you're debugging your code. Sometimes your code's not working, you can look at the code, you can throw in some print statements, and you can figure out what's going on. And here, you know, I could write a print statement to print out first arrow data, print out first arrow next, and so on. But that's not always going to work. And here's the reason.
It's also very tedious
It's also very tedious.
in my experience.
Yeah, but it's so rewarding when you figure it out. All right, let me make a new copy of this program list. Let me make a linked list called temporary, temp. And let me set temp equal to get node, and temp data equals 2, and list next equals temp. Let me get rid of these comments now, since we're not calling it first. Okay, so far I haven't changed anything except the variable name. So list is the initial Sentinel node from init. Temp is the return from get node, so it's a temporary node. Set its data equal to 2, and then have the Sentinel point to temp. All right, I had been saying let's make a new variable called second and set that equal to get node. I don't need a new variable. I can reuse temp. And this is counterintuitive. I can say temp equals get node and temp data equals 7. And when I say temp data equals 7, that is a totally different location in memory from when I said temp data equals 2. Because here temp was whatever address get node returned. Down here, temp is a different value. It's the value that this call to get node returned. Remember, every time I call get node, I get a new location in memory. A different array index from TA1. So in prior code, right, a variable was a variable was a variable. If temp was just a struct node and I said temp.data equals 2, and then later I said temp.data equals 7, that 2 would be lost. Not the case here. So this is what I mean by dynamically allocating memory. Temp down here is a totally different struct node from what it was up here. And that's a little weird to think about sometimes. Okay, so list is pointing to our first node. We need our first node to point to our second node. So I'm actually not going to do this. I'm going to say all right, make sure I don't bungle this. List is our sentinel node, temp is our first node, data is there, list is pointing to our sentinel. Okay, so temp is our first node with a 2. So I'm going to do this. I'm going to set temp's next field to be the address of a new node. And then I'm going to set temp equal to temp next. So let's go through this. List is an initial node. So I'm just drawing a sentinel node. I'm setting temp to the result of get node. So I'm right here. So I have my list node and I have my temp node. I'm setting temp data to be equal to 2. So that's putting a 2 right here. And then I'm saying list next equals temp. So that's setting up this pointer. Okay, now the magic happens. I'm going to say temp arrow next equals get node. Okay, when I call get node, that creates a new node in memory somewhere. When I set temp arrow next equal to that, that makes this thing point to that new node. And now when I say temp equals temp arrow next, I change temp to be equal to this. And now when I say temp arrow data equals 7, temp is pointing to this node, so it puts a 7 in there. Well, I'm going to repeat this. I'm going to say temp arrow next equals get node. It's going to make a new node, and it's going to have this point to there. And then I'm going to repeat this. And that's going to change temp to this node. And then I'm going to repeat this. And that's going to put a 14 in here. So I've only got one temporary variable called temp, but I've created 3 nodes and I've linked them together. Alright, so now I got a list of 6 nodes. So I'm executing the same code over and over and over again. And if I didn't want to just hardwire values, right, I could put this in a loop and I could say get an integer from the user, set temp next equal to get node, set temp equal to temp next, set temp data equal to whatever that number was that the user entered in. Right, and I could build a linked list of user inputs. Okay, so let's have our last node be the last node of the list. So instead of setting temp next equal to a new node, let's just set it equal to null. Oh, I went too far. Or I didn't compile it. Oh, I didn't run it right.
You also want to compile with list 2.c.
Thank you.
Oh, and to spare you from the arthritis, if you hit enter right after doing a command in Gdb, it'll repeat it.
Yeah.
So it's like an empty enter.
I logged out somehow. Sorry, what was that again?
So when you're in Gdb and you do a command, I think it's only if it's like incremental commands like next and step. If you just hit enter,
Right, it'll do the
just
same
go.
thing.
Yeah, and it is so good for your hands.
Yeah, yeah. All right, so let's run through. Thank you. All right, and we said temp next equal to null. All right, so list is 60, 20, 10. It points to 60, 20, 30. Well, let's just let's look at it in memory. So there's our sentinel node. There's the first node of our list. It's at location 60, 20, 30, which is over here. There's the data value 2. There's the next node, 60, 20, 50. Which is down here, data value of 7. Next node is 60, 20, 70, which is down here. There's 14. Next node is 60, 20, 90. 60, 20, 90, we find 22 with the next node of 60, 20, B0, which is down here. There's our negative whatever value. And the next node is 60, 20, D0. D0, we've got our data value of dead beef, and the next value is null. That's the end of the list. So we can build these lists by hand, right, pretty easily. Let's make a print function. So I'm going to call print. I'm going to pass it a pointer, which points to my sentinel. So what do I want to do? Well, I want to move to the next node because I don't want to actually print out my sentinel value. So I'm going to say pointer equals pointer next. And then I'm going to print pointer data. And then I'm going to say pointer equals pointer next, which will change to here, and print pointer data, and so on. So I'm going to basically do a loop. Move to the next node, print out the data, move to the next node, print out the data.
Just be while pointer does not equal null.
Yeah, but let's be naive. Let's do an infinite loop. Let's just loop through, and we're going to segfault at the end. But that's okay. We haven't had a segfault yet today. Let's move to the next node, print out the data value. All right, so let's prototype this function. And at the end of this, let's call print. Alright, there's our data values, 2, 7, 14, 22, negative 1, 11, dead beef. Now we got our seg fault. So yeah, how do we avoid that seg fault? It's an edge case question, right? So I could do well, pointer is not equal to null. That's actually going to work well. But depending on how you do this, for example, if I start off by moving pointer to the first node outside this loop, then this may not be what I want. But basically my idea in my head is PTR is always the node whose value I'm about to print. Okay, so PTR is the sentinel node. If that's not null, then I'm going to move to the next node. So this is not exactly what I want. Right, I still seg faulted. So if I'm thinking PTR is always the node whose value I am about to print, let's initialize this by setting PTR to be the first node. And if that node I'm about to print exists, if it's not null, let's print out its data value, and then change PTR to the next node. Okay, again, don't memorize this. Try some different versions of this, see if it makes sense.
Couldn't you have just said while PTR next
is not null.
Yep,
Yep, that's another way to do it. So this is where seg faults will happen, right? And if you've got 200 lines of code, it's really in these, like, 2 or 3 lines that your issue is. So nail this down first, right? And it will take multiple tries at doing this, but eventually it will become pretty natural to be able to do this and get all the data, including the first node and the last node, and not get a seg fault. It's an edge case question. It's too easy to start too soon and seg fault, start too late and miss the first node, stop too soon and miss the last node, stop too late and get a seg fault. You gotta nail it down just right on those. All right, so I'll copy this code over to the server. Also, the A section I called it main, this one I called it list, for what it's worth. All right, so we need to talk about freeing memory. I talked about that last section, but we'll talk about that on Friday in here. And then Friday we'll start talking about PA2 in detail, but it's the same as PA1. It's just using dynamic memory instead of an array. So we'll go through that, keep up with the ODPs, they'll be coming one a day through Saturday morning, and then we'll start up next week. All right, so see you next time.